Hello everyone, welcome to Tuteetute. In this particular video, we will see some of the important questions regarding the EMF. Okay, and this particular preparation you can able to take for the TS GENCO 2023. So first question is, charge needed within a unit sphere centered at the origin for producing a potential field V is equal to minus 6 into R power 5 by epsilon naught. Okay, and this is valid when R is less than 1. That means R range we can able to take from 0 to 1. And what they have given the potential field is nothing but V is equal to minus 6 into R power 5 by epsilon naught. You can know that units are volts. Okay, and this particular charge we have to keep at the center of the origin. For that purpose, when you have the potential, how to get the charge or charge density means using the Laplacian equation or using this particular Poisson's equation we can able to get. If you observe the Poisson's equation, we can able to take like this: del square V is equal to minus rho V by epsilon. So this is the Poisson's equation. So using this particular thing, we have V. So we can perform del square V. Epsilon is anyway constant only, so we can get the charge density. Once you have the volume charge density, we can able to get the charge by performing the volume integral of that one. Okay, this is the procedure we are going to apply. So using this equation, we are going to get epsilon, this rho V, and then the charge can be obtained by performing the volume integral of this volume charge density rho V. So these are the two things we need to apply in this particular question. Okay, so but if you observe this potential what they have given, that is in spherical coordinate system. How to tell that one? It is involving this R. In spherical coordinate system, the coordinates are R, theta, phi. So here it was written in terms of simply R. Theta and phi are not there. So it is easy for the calculation. So I am concentrating on this del square V now. So here you can able to see. So del square V is equal to, we can write del dot del V. So V is a scalar actually. Okay. So del V is the gradient of V. So it is a vector. So on this vector we can perform the divergence operation. Okay. So in this way we are going to do. Okay. So first I am writing del V. So del V is nothing but gradient of V. For that the formula in general is given by 1 by H1 dou by dou U. Whatever the scalar quantity we are taking, that one we have to take here, that is V. Okay, V can be a function of x, y, z if it is represented in Cartesian coordinate system. This V can be the function of rho phi z if it is represented in cylindrical coordinate system, or V can be the function of r theta phi if it is represented like this in spherical coordinate system. So we are using spherical coordinate system, but I am giving the general formula. Okay, so this is the first quantity, then we have to take, because the resultant of the gradient is the vector, here u cap we have to write. Okay, plus 1 by h2 dou v by dou v. This is another, this is a capital V I am taking. Okay, this UVW is nothing but r theta phi, but this numerator V is representing our potential field, like that you can able to consider. Okay, and it is a V cap plus 1 by h3 into dou v by dou w cap. But fortunately in our potential field we don't have phi component and theta component. Okay, phi, it is not a function of theta and phi. So we can able to remove these two things. So we can able to write only for this one. So what we are going to get, it is equal to the first scaling factor in case of the spherical coordinate system is h1 is equal to 1 only. Okay, h2 is r, h3 is r sin theta. So it is simply 1. So dou by dou r of what we have in place of V, minus 6 into r power 5 by epsilon naught. So it is equal to minus 6 by epsilon naught. R power 5 derivation with respect to r is 5 into r power 4. So this is equal to, we can write minus 30 by epsilon naught into r power 4. This is just gradient. Now on this gradient here, because it is a vector, we need to represent here unit vector also. Here u cap is there, na, that is nothing but r cap. Okay, So this is the vector. Now on this vector we need to perform the divergence, then you are going to get del square V. Okay, so now I am writing the divergence formula, that is del dot del V is equal to, and here also since we have only one component, the first component you need to write in the divergence formula. Okay, because it is changing only with respect to R. So what is the formula generally? 1 by H1, H2, H3 multiplied with dou by dou U of the second scaling factor and third scaling factor multiplied with the first component of the vector for which we are calculating the divergence. So what is the first component here? This entire thing is the first component only, na? So that is what I am writing here, or simply, okay, I will write that one only, minus 30 by epsilon naught into R power 4. Now you can able to take H1, H2, H3 values as 1 or R sin theta, then it can be written as 1 by R square sin theta, and here we will get H2, H3 is again, what we will get? R square sin theta. So dou by dou R of R square sin theta, okay, R square sin theta, this is minus 30 by minus 30 by epsilon naught into R power 4. This is what we got. Okay, now it is equal to whatever the constants are there, that I will write outside, but in front of this one we have already 1 by R square sin theta. Now what are the constants we have? We are performing the derivation with respect to R, so sin theta is the constant. So minus, now I am writing sin theta outside and 30 also outside by epsilon naught, that is also outside. Okay, now what is there within this particular derivation? Within this one, R power 6 is there, R square multiplied with R power 4, that means R power 6. So if you perform the derivation of that one with respect to R, you will get 6 into R power 5. Okay, so derivation is over, that means you have now del square V. Okay, so this left side part you have achieved now. Okay, and here we can able to cancel the sin theta can be cancelled, and here R square, if it is cancelled with R square, we are going to get a R cube. Okay, so finally what did we get here? It is equal to, minus is there, and 30 into 6 is 180 by epsilon naught into R power 3. This is what we have. Okay, this is del square V. Now it must be equated to minus rho V by epsilon according to this Poisson's equation. So it is equal to minus rho V by epsilon or epsilon naught. You assume we are in the free space. So these two will be cancelled, minus will be cancelled. So rho V is equal to, we got here 180 into R power 3. So this is what we got. But this is not the answer. They asked about the charge. So as I said previously, using this rho V, we need to get the charge. Okay, by performing the volume integral. Okay, that is what we are going to do now. So charge is equal to volume integration of rho V dV, and we are working in spherical coordinates. So when we work in spherical coordinates, here r theta phi are the coordinates, so r value should be changed from 0 to 1. According to the given data, r is less than 1. So r should be taken from 0 to 1, and theta in general it is taking from 0 to pi, and phi range is from 0 to 2 pi. Okay, theta range is just 0 to pi only, but phi range is from 0 to 2 pi. And rho v, how much rho v we got? 180 into r power 3. This is rho v. But dv is nothing but we have to take differential lengths due to the changes in r, due to the changes in theta, due to the changes in phi. So what we'll get here? R square sin theta dr d theta d phi. So once you check your basics related to this spherical coordinate system, when you change dr, the scaling factor is 1 only. So just dr will get. When you change theta, the differential length will get r d theta. When you change phi, the differential length is r sin theta d phi. So if you multiply these three, we will get here r square sin theta is the extra factor we will get here, because due to d theta we will get r, due to d phi we will get r sin theta. So r square sin theta is the extra thing we are going to get. Okay, so it is equal to, now 180 is constant out of all these things, and here we have r power 5. Okay, and we need to perform the integration of r power 5, so that is 1 by 6 into r power 6 with limits 0 to 1. Okay, next sin theta integration is minus cos theta, and limits if you substitute you will get minus 2, so minus into minus 2 is plus 2, and integral of 1 with respect to 5 is 5, and limits if you substitute you will get 2 pi. So this is about the integration, and here also if you substitute the limits you will get 1 only. Okay, so finally we can able to write 6 into 30 is 180, so it is equal to here 30 into this is 4, that means 120 pi. So 120 pi coulombs is the answer. Okay, so in order to perform this particular problem, what you need to know in the sense, you need to have some command and the spherical coordinate system, how to take differential volume and what is Poisson's equation. Immediately you should get the idea, because the question is related to charge and potential. Okay, charge and potential means these two are related by using our Poisson's equation only, and using this one you will get here actually this volume charge density you will get, and if you perform the volume integration of that one you will get the charge in coulombs you will get. Okay, now we'll see the next question. A solid cylinder conductor of radius capital R. Okay, so we have to take one cylinder. Okay, and it is having a radius is capital R. This is side view. If you see from the top, it will be looking like this. Okay, circular cross section will be there. So if you see from the top, you can able to observe this is the cylinder. Both are same cylinder only. Okay, has a uniform current density. That means from total length of the cylinder same amount of current is passing. So uniform current density is available. Uniform current density. And the radius is R, that is also we have given. The magnetic field H inside the conductor at a distance R from the axis of the conductor is. They are asking about the magnetic field inside the cylinder. Okay, inside the cylinder. For that they are representing with respect to the distance R. That means small r is variable actually. You need to know what is constant, what is variable. So small r is the variable. So R can be taken from 0 to capital R. When you take capital R, this is directly the surface of the cylinder only. Okay, you need to take this range. But when you take small r, it can be anything from 0 to capital R. That means we are representing with this dotted one, which is representing small r. Okay, so this is what you need to understand. But when you consider the complete radius capital R, that is related to some current, uniform current, we can consider that is capital I. But what is the current related to this small r is nothing but it is surely different. So understand this point. Okay, this point is very, very important to solve this particular problem. So they have given one cylinder with the radius capital R, and that particular cylinder is having the uniform current density or uniform current. Okay, I am representing with capital I. That means capital I is related to the radius capital R. But what is the current related to small r? Small r can be any radius starting from 0 to capital R. So it is a variable. So this current is different related to small r. So we need to get the relation among these four things now. Okay. So assume this current is, for example, I dash. So generally it is a cross-sectional area is, what type of cross-sectional area is there? Circular cross-sectional area is there. Why I am taking circular cross-section only? They told that uniform current density is available. So density means with respect to area we have to calculate. So I is related to pi r square. So I dash is related to pi small r square. Okay. Now just cross multiply this one. So what you will get here? I dash is equal to pi will be cancelled. So I dash is equal to I r square by capital R square. You see, when small r is equal to 0, total current is equal to 0. Small r is equal to 0 means there is no cylinder. Okay. But when you take small r is equal to capital R, we are concentrating total cylinder. So total cylinder means already whatever we have given, that should be satisfied. So when I take small r is equal to capital R, these two will be cancelled, the current should be equal to capital I. But whenever some other value we are taking for R in between 0 and capital R, this particular current is lesser compared to capital I. So this is the relation we need. Now we will see the rest of the question. Okay, the magnetic field H inside the conductor we need to calculate. So magnetic field H we have to calculate using this current relation, means which law we have to apply? Ampere's law. So Ampere's law is relating magnetic fields and its source current. So the Ampere's law is given by closed line integral of H bar dot dl bar is equal to I enclosed. Now we are concentrating on this particular radius small r only. So what current I have to take? Here already I have calculated that is I r square by r square. Okay. So why I am not taking total current I? Because we are calculating through the small radius r only, not capital R. Okay, only small r, not complete cylinder we are not taking. Okay, that is what you need to concentrate. Now how to take this closed line integral, you see carefully. And we know that when current is passing, for example here current is passing upside, capital I is passing upside, then using the right hand thumb rule, if you keep your right hand thumb in the direction of the current, then these four fingers are representing the direction of the magnetic field. So if you keep like this, then it is these four fingers are in the direction of phi direction. Okay, in the rho phi z you can able to take in the phi direction, we can able to have this magnetic field. That means this magnetic field is circulating around this particular conductor. That is what we need to understand. That means what is the direction of the magnetic field? Phi direction. So here I am taking closed line integral of this h bar is nothing but h phi a phi cap. Okay, so h bar is having only one component, that is phi component, so that I have written like this dot. Now this rho L also we have to write that particular whatever the phi direction is there, in that we have to write differential length vector. So that is nothing but that is due to the changes in d phi. But d, when you have the changes in phi, what is the differential length? Rho d phi. Okay, that is what basics from the cylindrical coordinate system. But here they have represented this radius with r. So we no need to represent with rho. I am also representing with small r only. Okay, so based upon the problem, wherever it is required, we need to change the letters. Okay, so now a phi dot a phi is nothing but 1, because both are unit vectors in the same direction. So we will get dot product is 1. Now, and this particular h phi is constant only, we can take out of the integral also. So h phi is constant, we have taken out of the integral, and we can take this r is also constant with respect to phi. Now integral phi limits are changes from 0 to 2 pi. So integral of d phi is nothing but we will get here 2 pi. So it is equal to what we get here, I into r square by capital R square. So this r will be cancelled. So h phi is equal to, we got here I r by 2 pi r square. So finally we can able to write h bar is equal to IR by 2 pi r square. This is a h phi component na. So here a phi cap we can write. So in this way we have to solve. So here main important thing is you should not consider the total current I or total current density J. Okay, like that we can consider total current density J for the radius R. Okay, that is possible. You can take capital complete current density J or complete current I you can consider when radius capital R is available. So it is required to calculate how much amount of current is there for the small radius small r. Okay, so that is what we have performed here. After getting this one, just applying Ampere's law is enough. Okay, so this knowledge is required in order to solve this particular problem. Now we'll see the next question. The question is related to Faraday's law. In a 100-ton coil, so immediately we can able to write the data, that is number of tons is equal to 100. Okay, capital N is equal to 100 I have taken. If the flux through each coil is given by, so magnetic flux phi m is equal to t cube minus 2t, they have given as a function of time and flux means it is in Webers, so they have given in milliwebers. Okay, so the magnitude of the induced EMF in the coil at the time of 4 seconds is, okay, so we have to calculate induced EMF at t is equal to 4 seconds. 4 seconds. So using the Faraday's law we can able to write. So we should have the knowledge of different laws in the EMF, and we need to remember each law is giving what type of relation. In between what variables we have the relation. That is what we should get the idea. The question is related to this Faraday's law, because the question is talking about EMF and flux, magnetic flux. So surely we know that from the Faraday's law, we can able to write induced EMF is equal to minus dou phi m by dou t. That means it is clearly giving the information that rate of change of magnetic flux producing the EMF. That is what it is giving the information. Okay, but it is valid when only one turn coil is there. Okay, only one loop is there, it is valid. But in the question they have given, it is having 100 turns. So where we have to do the modification here? Here we have to keep the number of turns capital N. Now based on this, easily we can able to solve. And here derivation is to be done with respect to t, and they have given phi m also in the as a function of t cube minus 2t. So as it is, we can able to apply. So minus number of turns 100 multiplied with dou by dou t of phi m. Phi m is nothing but t cube minus 2t milliwebers. Okay, milli means 10 power minus 3. So minus 100 into 10 power minus 3 I am writing here. Now I am going to perform the differentiation of this function with respect to t. I will get t 3t square minus 2. Okay, but it is to be calculated at t is equal to 4 seconds. Okay, so apply that one. So it is equal to minus, it is 10 power minus 1, and here we will get 3 into, so 4 square is nothing but 16 minus 2. So it is equal to, how much we will get here? It is 48 minus 2, 46 is nothing but here 4.6 volts we will get. Okay, so in this way we can able to solve. If you know the Faraday's law, we can able to solve this one easily. Next question. A positive charge of q coulombs is located at point 003. That means it is available on the z-axis, positive z-axis. Okay, and charge is capital Q, and negative charge of magnitude capital Q coulombs is located at point 00 minus 3. You see, plus Q is available at 00 plus 3, and minus Q is available at 00 minus 3. That means both charges are available on the z-axis only. But one is at 003 position, second one is at 00 minus 3 position. The electric field intensity at point 400. Okay, 400 means it is available on, this point is available on positive x-axis. Okay, so that is in the direction of, in which direction the electric field is there. We no need to calculate how much electric field is there at this point, but we are required to calculate the direction of electric field at this particular point. Okay, so these things we can able to understand in a better way by drawing the diagrams. Okay, so since we are working with the z-axis and x-axis, I am drawing those two only. Okay, no need to take y-axis, because two charges are available on the z-axis. That means it is required to have positive z-axis and negative z-axis, and the observation point is on the positive x-axis, like that I have taken. Okay, first I am indicating the observation point that is available at 400. So this is the observation point where we need to calculate the direction of the electric field. Okay, next first charge is available Q, actually that is at 003, and second charge is available, that is minus Q, available at 00 minus 3. This is the given data. Now we are required to calculate the direction of electric field at 400. Okay, so it is about completely direction. Okay, it is completely about the direction only. So, but where we have to concentrate in the sense the sign also. Okay, sign of the charges also. Otherwise, there will be a mistake. Okay, so actual thing is what? For example, if you see the Coulomb's law, if you observe the definition, okay, if you see that particular law, the force in between the two charges is directly proportional to the product of the two charges. Force is inversely proportional to the square of the distance. Okay, and one more point is there. The force is along the line, okay, which is joining the 2 points or 2 charges. Here also we have to take the same thing. Whether it is electric field also we have to take same thing. So the electric field is along the line which is joining the 2 points. Okay, one point is observation point, second point is the source point. Okay, so that is the key point here. Electric field is along line which is joining 2 points. This is a key point. Okay, so because of Q, in which direction electric field is available, that we will see first. So this is the source point, this is the observation point. So this electric field is available along the line which is joining these two. But because it is the positive charge, it is diverging in nature. The electric fields are coming out of that particular positive charge. So it will be in this direction. That is the very, very important point. Now you leave it about this plus Q. Now concentrate on minus Q. Okay. So again, this is also source point. Here observation point is there. Again, we can apply this particular statement. The electric field is along the line which is joining the 2 points. Here one point is there, here another point is there. So we have to take the direction is along the line which is joining these two. But is it going outside or is it is coming into the minus Q, means it is going into the minus Q because it is a negative charge. So electric flux lines are going into the negative charge. So the direction will be this side now. Okay, now superposition principle we have to apply. In the system, we don't have single charge. Okay, we have 2 charges. So because of plus Q and because of minus Q, the electric field is available at the observation point 400. So what is the resultant electric field direction means? We have to take vector addition of these 2 directions. Okay, so simply here I am drawing the resultant thing is like this. So this is the direction of electric field due to minus Q. This is the direction of electric field due to plus Q. Now the resultant direction will be like this. Okay, that means it is in which direction? Negative Z direction. Positive Z direction means upside, negative Z direction means downside. So we can able to tell that now the resultant electric field is along negative Z direction. So like this we can able to answer. So this is the answer. Okay. Now the next question. The force between 2 point charges of 1 nanocoulomb each with a 1 mm separation is in air. That is what we have to calculate. So it is related to, simply we can able to tell Coulomb's law. Okay. So Coulomb's law means F bar is equal to 1 by 4 pi epsilon naught. 2 charges product we have to take Q1 Q2 by the distance between these two, that is magnitude of R square into R cap. This R cap we can able to write in the normal form, that is 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R square. This unit vector if you write in the normal vector form, R bar by magnitude of R. So it is equal to 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R cube into R bar. You see, when you have here unit vector, you will be having here square of the distance only. But when you have here normal vector R bar, then in the denominator you will be having cube of the distance. Which one is to be preferred? Okay. At this particular moment, why I have taken this particular question means you will get the clarity regarding this formula or this formula. Which one we have to use in this type of questions. Now you observe the question carefully. They asked about only the magnitude of the force. They did not ask about direction, because you can see, okay, where we have the charges we don't know. Simply they have given in between the 2 charges 1 mm separation is there. That is what they have given. But where is that, where are that particular 2 charges we don't know. Okay, so they are asking about only the magnitude. So if you see the Coulomb's law definition also, the force is proportional to product of the 2 charges. The force is inversely proportional to square of the distance only. Okay, in the definition, if you see carefully, it will be given as the square of the distance only. But by modifying the formula, you may see here cube of the distance. But this one we should not use. Okay, in the calculation process, you can able to use where you don't have here this particular unit vector. Unit vector will not be there here. So, basic thing is this one. Okay, basic thing is this one. When we need the magnitude, surely you have to take this part only. When we need the magnitude, surely you have to take here this part only, and here you need to keep r cap. That is what you should not forget about that one. Okay. So now in this particular question, we are going to calculate only this part. Okay. And in the air they are saying, that means approximately free space. So 1 by 4 pi epsilon naught, we know the value, that is 9 into 10 power 9. That is multiplied with the product of the two charges, and each charge is 1 nano coulomb only. 1 nano means 10 power minus 9. Second one is also 10 power minus 9. By distance, clearly they have given 1 mm, 1 millimeter. That means 10 power minus 3, 10 power minus 3. So this is what we have to perform as the calculation. That's it. Okay. So magnitude of the force is equal to, that is equal to, so this nano and this 10 power 9 will be cancelled, and 9 into, here we have 10 power minus 9, this is 10 power minus 6, if it is going to the numerator, you will get 10 power plus 6. So it is equal to 9 into 10 power minus 3, that means 9 millinewtons. This is what we can able to calculate. Okay. Now the next question is, an infinitely long uniformly charged density of 30 nanocoulombs per meter. So if you see the units, 30 nanocoulombs, that is nothing but nanocoulombs per meter means this is line charge density. Okay, what they have given, line charge density rho L is equal to 30 nanocoulombs per meter. This is what they have given. Okay, is located at y is equal to 3 and z is equal to 5. Okay, available at y is equal to 3 and z is equal to 5. Generally, in a three-dimensional space, okay, for example, since already they have mentioned yz, we can work with respect to Cartesian coordinate system. If I give three values, x is equal to something, y is equal to something, z is equal to something, then that three values are representing one point in the space. But if I give only one value, okay, that is representing the plane. If I give two values, that is representing the line. These are the basics regarding the Cartesian coordinate system. So what we need to understand here, y is equal to 3 is actually the plane, two-dimensional plane. That plane is parallel to xz plane at the distance of 3 units. Z is equal to 5 is the xy plane. Okay, it is parallel to xy plane at the distance of 5 units. That is what we need to understand. So if I give these two, the intersection of these two planes will give line. That line is available at y is equal to 3 and z is equal to 5. What about x value here? X is changing from minus infinity to plus infinity. So understand this one very carefully. Okay. For your understanding, here I will take one graph. For example, x, this is y. Okay. And z is coming out of the plane. Otherwise, we can work with respect to the given data only. So anyhow, I will take this one. Okay. Now I am saying that x is equal to 1, y is equal to 2. This is example thing only. Okay. X is equal to 1 means the plane will be available here. Okay. This is 0, this is 1. So the plane will be available like this. X is equal to 1 means z-axis is coming out of the plane. Z-axis is coming out of the plane. This particular board is representing the xy plane. This variation is x, this variation is y, z variation is like this. Okay, so board is xy plane, but how to represent x is equal to 1? X is equal to 1 I have taken, so like this I can represent x is equal to 1. This is x is equal to 1 means actually it is parallel to yz plane. You see this is the yz plane, na? Y is this one, z is this one. So this is yz plane. Now we are moving 1 unit distance from the yz plane and we are saying that is x is equal to 1. Okay. Now y is equal to 2. So y is equal to 2 means y is equal to 1, y is equal to. Now this is y is equal to 2. Okay, y is equal to 2 is parallel to xz plane. Okay, this is y is equal to 2. this is x is equal to 1. Intersection of these two will give one line like this. Okay, intersection of these two will give one line. That line is actually parallel to z-axis. See carefully. This is x is equal to 1. That means throughout this infinite distance it will be there, upside, downside, and towards this side and going into the board also. Now y is equal to t is this one. Infinite distance it will be there, coming out of the board infinite distance. Now this one is intersecting with this one. Then what will happening? Only one line will be there. That line is coming towards you, and that line is parallel to z-axis. Okay, here one line is there that is coming out of the board like this, going into the board like this only. That is exactly parallel to z-axis. This visualization is important. Okay, so now we can able to tell what is this one. This is not point, this is line. Intersection of two planes will give one line. So that is what we need to follow. To explain this one, I have taken xy plane and the line is parallel to z-axis. But in the given question, the line is created because of the y is equal to 3 plane and z is equal to 5 plane. So you forget about this one. Now I am going to draw using these two. So I am taking here y axis, here z axis, y is equal to 3, this is z is equal to 5. So y is equal to 3 is this plane, z is equal to 5 is this plane. So x axis here it is coming out of the board. So this is nothing but the given line. This given line is having the line charge density rho L is equal to 30 nanocoulombs per meter, and this given line is parallel to now x axis. Given line is parallel to x axis. This is the thing you need to understand. Okay, so instead of taking like this, you can observe like this also. Okay, we can take here. Otherwise I will take only positive axis only. So like this I am taking. Okay, so you take it is x axis, this is y axis, this is z axis. What they have given, y is equal to 3. So y is equal to 3 means here y is equal to 3 will be there, and z is equal to 5. Z is equal to 5. So you can take like this, and you need to draw one line like this. The intersection of these two will be like this. You see the resultant line is parallel to x-axis. Okay, so like this we can observe, or like this we can able to observe. So the thing is, the resultant line, that is the intersection of y is equal to 3 and z is equal to 5, is parallel to x-axis. That is the key point you need to remember. Okay, so that is the thing you need to remember. Okay, now we'll come to the question. An infinitely long uniformly charged density of 30 nanocoulombs per meter is located at y is equal to 3 and z is equal to 5. The field intensity at 0.61 is, they have given something. Okay, so E bar is equal to something they have given, that is 64.7 y cap minus 86.3 z cap volts per meter, and this is available at 0, 6, 1. Okay, now what is the field intensity at 561? What is the field intensity at 5, 6, 1? This is what we need to solve. Okay, so in order to solve this problem, this criteria you need to understand. Whatever the concept is there, that is what you need to understand. Actually, because of the infinite line charge, what is the electric field? Rho L by 2 pi rho epsilon A rho cap. This formula has been derived. Okay, when we consider the infinite line charge is available on the z-axis. Okay, and purely it depends on this rho. Rho L 2 pi epsilon is constant only. So electric field is actually inversely proportional to the distance. Okay, perpendicular distance. For example, the infinite line is like this. If you calculate electric field here, then you need to calculate, if you want to calculate the electric field at this particular point, you need to calculate the perpendicular distance. If it is 2, this rho is equal to 2, you need to substitute. Now you go to some other place. That means, for example, this is some point like 2, 3, 4 like this. You go to some other place. So this is 1, 2, 4. Okay. Here again you need to calculate the perpendicular distance. That thing you need to substitute at a row. So in the calculation of the electric field due to the infinite line charge, what is important means perpendicular distance is important. Perpendicular distance from the line charge is important. Okay. But so many points will be there at the same perpendicular distance. You can see like this. All these points are at the same distance only. Similarly, if you observe this particular question. Okay. This line charge is actually parallel to x-axis. That means here so many points around that particular line charge are at the equal distance only. Okay. Why I am telling this one? This is the electric field they have given at 0, 6, 1. Where it is available actually? It is available on the YZ plane only. Na? X coordinate is 0. X coordinate is 0. So at 6, 1. Y is 6. Z is 1. That means here. So this is the perpendicular distance. If you calculate this one, then using this particular formula, you will get this one. This is what they have given. Now what they are asking? We need to calculate the electric field at 5, 6, 1. If you observe, the Y coordinate and Z coordinate both are same. Only X coordinate is changing. Now you observe carefully. This is the line. Previously, this is a given electric field at 0, 6, 1. Now what we have done? X value we have increased up to 5. But Y and Z values are same. This is 0, 6, 1. This is 1, 6, 1. This is 3, 6, 1. This is 5, 6, 1. This is the 5, 6, 1. Again having the same perpendicular distance. Okay, parallelly we are moving. Along this particular given line charge, parallelly we are moving means this point is also having the same perpendicular distance. Because same perpendicular distance is there, you will get the same electric field. So there is no change in the electric field. Given electric field itself is the electric field at 5, 6, 1 also. So in order to solve this particular problem, you need to know the criteria. You need to know the concept. So the electric field basically depends upon the distance only. What is the distance? Perpendicular distance from the line charge towards the observation point. Like that you will be having the so many points having the same distance from the line charge. So all those points are having the same electric field only. So the question is related to that particular concept. Okay. So here that particular line charge is actually parallel to x-axis, and along that particular x-axis only the observation point is changed from 0, 6, 1 to 5, 6, 1. So the 5, 6, 1 point is also having the same perpendicular distance. That's why electric field is also same electric field we will get. That is what you need to understand. Okay.